Every year, the world produces over 1,800,000,000 tons of steel. That's enough to build thousands of bridges, but only one of them will become North America's longest cable-stayed bridge, the Gordie Howe International Bridge. 125,000 tons of metal, over 1,000,000 bolts, and a span of nearly 3,000 feet with not a single support in the water. How do two countries stitch steel together over a river? And what happens if even 1 millimeter goes wrong? Stick around to the end, and you'll see the moment when American and Canadian metal literally kiss in the sky. The birth of the steel backbone for the Gordie Howe Bridge starts long before the first beam reaches the construction site. This is a cross-border industrial operation where the Canam Group plays the starring role. The steel for this project isn't just metal. It's the result of collaboration between American and Canadian steel giants. Sheets of high-strength specialty steel are forged at mills in both countries. Then massive rail cars funnel them towards specialized fabrication shops. When you walk into a Canam plant, the first thing that hits you is how modern robotics tames raw matter. You won't see blacksmiths with hammers here. Laser systems and giant computer-controlled machines rule this space. Steel plates several inches thick are cut by laser or plasma with precision down to tenths of an inch. That's critical because each edge girder is made up of dozens of elements that must fit together perfectly during welding. The most dramatic moment at the plant? Assembling that famous box girder beam. Massive magnetic cranes hoist steel plates 49 feet long and position them into specialized assembly jigs. Here begins a process engineers call submerged arc welding. It's an automated technique where the welding head travels along the seam, hidden beneath a layer of special powder, flux. This prevents metal spatter and ensures perfect joint quality. Inside, the beam is reinforced with countless stiffener ribs. These are vertical steel partitions that prevent the structure from deforming under the colossal weight of the roadway. Every weld passes through the hands of inspectors armed with ultrasonic and X-ray flaw detectors. On the Gordie Howe Bridge, there's no room for average quality. If they find even a microscopic air bubble inside the metal, the part gets rejected. After welding, the finished beam heads to the shot blasting chamber, where its surface gets cleaned to a shine, then receives multiple layers of special polymer coating. This is armor against moisture and salt, designed to protect the steel for 100 years. Folks, check this out. I'm standing at a safe distance right now, but even from here, this thing looks completely unreal. We're used to the word beam, but on the Gordie Howe International Bridge project, that term takes on a whole new meaning. Each of these edge girders is a 100-ton steel titan that's literally twice my height. I've watched them get moved. It's a full-on special operation. Giant multi-axle platforms creep slowly across the construction site, and the gravel literally buckles beneath them. When they lift one of these beams into the air, it blocks out the sky. That's the moment you realize there's nothing impossible in this world for someone who's learned to tame steel at this scale. This is pure, raw, 100-ton power that's about to become part of the longest cable-stayed bridge in North America. Ever build with Legos as a kid? Now imagine one piece weighs 100 tons, and instead of plastic connectors, you've got a blazing welding arc. We're on the banks of the Detroit River, and what you see behind me, engineers call an assembly node, but I'm calling it a playground for giants. The assembly process for the Gordie Howe International Bridge means building giant modules right here, on the ground. You can't just hoist one beam and clip it together in the sky. First, on special steel jigs along the shore, these 100-ton edge girders get welded into single sections. It looks incredible. Two parallel edge beams connected by cross-steel trusses, forming a massive frame. When a section's complete, it resembles part of an aircraft carrier deck that someone decided to build in the middle of an industrial zone. Why do they do this on shore? Because here, welders have something they don't have at 492 feet up: stability. Every seam, every joint has to be perfect. I walked up to these guys. They're working in special masks with fresh air supply because the welding intensity here is so high that the air around them literally burns up. You see these welds? They're as wide as my palm. Robotic welders pass dozens of times over the exact same spot, laying down layer after layer to create a monolithic joint that no storm will ever tear apart. Now look at these bolted connections. Where welding can't be used, thousands of high-strength bolts take over. Each one is tightened with such force that the steel plates start working as a single unit through friction force. When a section like this is fully assembled, they check it with laser scanners. Accuracy has to be within an inch. If there's even a hair's width of misalignment, literally the thickness of a matchstick, then midway across the river, when the Canadian side meets the American side, they just won't line up. The feeling of being next to one of these sections? Pure adrenaline. You're standing inside a steel box that's about to hang over a gorge, carrying thousands of people. The sound here is something else. Constant grinding of metal, hissing of pneumatic tools, and the rumble of heavy cranes. Across the water, slow and almost silent, a massive barge glides forward. Resting on its deck is the very section we saw on shore. A steel frame with edge girders weighing hundreds of tons. From the bank, it looks like a surreal steel island drifting between two countries. But the moment that barge locks into position directly beneath the bridge span, the air gets electric. You look up, and 150 feet above the water, you see the red jaws. Special lifting devices mounted on the edges of the completed spans. What engineers call the heavy lift is beginning. This isn't a quick process. When the winches start working, the steel cables tighten like strings on a giant guitar. You hear that sound? That low, guttural groan of metal accepting colossal weight. The section slowly lifts off the barge. The first few feet of empty space appear between the water and the steel bus. In that moment, all the weight of this monster bears down on the pylons and cables. You literally see the bridge settle a few inches, coming alive under the load. I stood on the shore, holding my breath. Surveyors with laser rangefinders track every millimeter of lift, second by second. And then, when the section finally lines up with the bridge edge, the most critical part begins. The iron workers, who look like tiny dots against the white beams, start catching the section. They use hydraulic jacks to perfectly align the bolt holes. This is the moment when American and Canadian steel has to kiss. When the first pin slides through both plates, a wave of relief you can physically feel washes over the construction site. Its main span is 2,799 feet. That's a massive pile of steel hanging over water with zero support in the river. That makes it the longest cable-stayed bridge in all of North America. Over 125,000 tons of structural steel went into this thing. Constant corrosion from salt water. There's colossal enough metal here to build 1.5 Kitty Hawk-class aircraft carriers. And what about the fasteners? Connecting all these massive beams took over 1 million high-strength bolts. Each bolt is a tiny guarantee that this backbone will handle 100 years of use and more than 2.5 million trucks every single year. It's a genuine metal ocean, tamed by human ingenuity. Did you enjoy this journey from cutting up aircraft carriers in Texas to the birth of new Titans in Detroit? If so, you know what to do. Hit that steel bell, smash the like button, and make sure to subscribe to the channel. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxins inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting, cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. What if I told you a single metal strand, thinner than an inch, can hold hundreds of people over a cliff, and know it every single second? Every year, the world builds structures that cannot afford to fail. Cables for gondolas, chains for cranes, reactor heads holding back pressure like the lid on a volcano. But almost no one knows why these things don't snap, crack, or kill. There's no magic here, just math, control, and processes nobody talks about out loud. In this video, you'll see how metal is twisted, welded, and pressed so it lasts for decades. And if you stick around till the end, you'll learn where the weakest point actually lives in any eternal steel structure, and why almost nobody sees it. The cables for the Pisval Grande A5 gondola systems by Fatser AG aren't simple ropes. They're multi-layer monsters with a diameter, as already mentioned, of less than an inch, made from high-strength wires with built-in fiber optics and data cables. Each individual wire in the strand and each strand in the cable has its own precisely defined twist pitch and tension. This process happens under constant sensor monitoring. Individual tension control prevents internal stresses that could lead to premature metal fatigue failure. Because the layers nest into one another with mathematical precision, the cable becomes less prone to stretching. Using high-strength alloys and precise braiding allows them to reduce the cable's overall diameter without losing breaking strength, which is critically important. To join chains, rods, and rings, a method called flash butt welding is used. The ends of the workpieces are brought together under high-voltage discharges. At the contact zone, a series of metal micro-explosions occurs, literally burning out all irregularities, oxides, and contaminants. This guarantees perfect surface cleanliness before joining. When the metal heats up to a plastic state, the machine executes a sharp impact motion, compressing the parts under enormous pressure. Atoms from both pieces form shared bonds, creating a monolithic structure that's just as strong as the base metal. The weakest point of any weld is the excess molten metal that gets squeezed outward. If left behind, it becomes a source of stress concentration and micro cracks. The built-in deburrer does its job instantly while the metal's still scorching hot. Special cutting blades flow around the part's shape, whether it's a ring or a link, shearing away excess metal flush to the surface. Because the removal happens in the hot state, the metal doesn't experience the mechanical shock that comes with cold grinding. The smooth weld lets the chain or ring glide through pulleys and guides without friction or vibration, a must for safe operation over decades to come. This synergy of twisting and precision welding creates structures that stand up to dynamic loads for decades, all while staying lightweight and cost-effective to manufacture. A steel pancake 5 inches thick. That's the blank for a Hemi head, the part that holds pressure in chemical plants like a lid on a pot of boiling volcano. At ICM WADA, they toss it into a furnace, heat it to 1832 degrees Fahrenheit. The steel goes soft like Play-Doh. Then a giant press weighing hundreds of tons shoves it into a metal die. Once, the pancake buckles. Twice, deeper still, 3 times, almost a hemisphere. Each pass takes 10, maybe 20 seconds because it cools fast, so back into the furnace and repeat. Then with a hammer, like in a blacksmith shop, they pound out the curve to make it even. Cool it slowly so it doesn't crack, normalize it in the furnace for strength, and ultrasound scans the inside, like an X-ray, catching bubbles or cracks. The finished head withstands pressure up to 500 atmospheres. Next is flanging. They lay flat steel on the table. The machine grabs the edge and bends it up like a can lid. 90 degrees, thickness up to 2 inches. Hydraulics press evenly. A computer monitors to keep it from bending crooked. For pipe joints, where a seal saves you from an explosion. Then a machine with 800 tons of force stamps in the curves. The part sits on the die. The ram comes down. Metal flows like dough, forming arcs or bowls in minutes. And in New Zealand, a 1,000-ton press brake takes a 20-foot plate. Bam! Bends it in half like a sheet of foil. Slowly, with a loud creak, shavings flying. Biggest in the country, cuts metal for ships or bridges without breaking a sweat. And for dessert, the Bronneberg Super 3, a scrap baler, like a compressor for metal. A box with toothed walls, steel, aluminum, cables get dumped in by the pile. A lid with knives drops from above, cuts everything like pruning shears, no pre-cutting needed. Hydraulics press it into a 3-foot cube. Oil heats or cools to prevent overheating. No foundation required, sits right on the ground, remote control operation. Press a button and out comes a bale, dense as a brick, weighing a ton. Easy to haul for remelting, saves space and gas. These machines are like recycling superheroes, turning trash heaps into fresh steel without the mess. Oxygen lance cutting of a 16-ton cast iron shaft. First, gondola cables. Not your ordinary ropes, but thick monsters the diameter of a beer can, woven from thousands of wires. Each cable is twisted separately, like braiding a giant rope, with built-in cables for internet and lighting in the cabins. They handle speeds of 14 miles per hour, cabins with people at skyscraper height, and last 40 years because they're lighter and cheaper to transport. Nearby, a machine welds chains and rods. You place the metal in clamps, an electric discharge strikes, like lightning, and the ends fuse into a solid seam. Then, a milling cutter removes imperfections in seconds, so there are no sharp edges that could injure or snag anything. Perfect for cranes and lifts, no cracks or warping. Next, a welder for reinforcing pipes. Takes rods, wraps them in a spiral of wire, changes the shape to oval, saves up to half the steel, but same strength. The machine spins, welds, feeds. Out comes a cage for concrete manholes from small to massive, no unnecessary manual work. Toyota crankshafts are cut from a solid metal billet, 5.5 inches in diameter. The machine mills the curves, turns the journals, balances the weights, drills the oil passages, all in one shot, no repositioning. Then furnaces harden it. Cold nitrogen makes it stronger. Grinding brings it to a shine. Perfectly round, zero tolerance. Giant lathe for train wheels. Locks the bogie, strips metal from wheels and brakes. Cast iron base kills vibration. Chips break down automatically, and the cars roll smooth again. No risk of derailment. Robotic machine with twin spindles. The robot grabs a fresh blank while the old one's spinning, turns it, mills the sides, cuts teeth, flips it to the other end, no stopping. Cuts pockets, contours, everything in one cycle, like a speed assembly line. Fatzer AG twists cables over 40 tons, locked coil ropes for bridges, plus spiral types with sockets. They produce complete batches of 420 cast terminals, ready for installation, for suspension structures like pedestrian bridges in Germany. Cage welders, BSM, ISM 250R models, turn out round or oval reinforcement for pipes, up to double layers without a second operator. Programmable spiral pitch, diameters from 13 to 142 inches. They save 50% on steel. For medium volumes, dozens of cages per hour, with touchscreens and LAN. Underfloor wheel lathes for train wheels, machine locomotive and car bogies under heavy loads. The portal passes straight through, reprofiles wheels and brakes, chips the shavings. Throughput, 20 bogies per shift depending on wear. Quick turn robotic machines slash cycle times by roughly 40%. Spindle hits 4,000 RPM. Y-axis travel, 4 inches. Grippers reach about 13 inches. Multitasking means one part in 10 minutes instead of hours. Fatzer AG is a Swiss outfit out of Romanshorn, founded back in 1836 as a hemp rope factory for ships and fishermen. Today, they're leaders in steel cables for mines, bridges, ski lifts. Take the Fury Trockener Stig ropeway in Zermatt. They shipped 2 cables, 70 tons each. Delivery through narrow bridges at night, full cycle from design to installation. They do turnkey cables, tension testing up to 750 tons, embedded fiber optics, splicing. Every year, billions of people around the world touch chromium, on faucets, cars, appliances, and almost no one realizes that behind this cold shine lies one of the most dangerous chemicals in modern industry. How can a metal that makes steel stainless and withstands jet engine temperatures simultaneously poison water, air, and the workers who handle it? In this video, we'll step behind the doors of mines, furnaces, and electroplating tanks. Witness how gleaming surfaces are born from toxic dust and molten metal, and by the end, reveal a property of chromium that even many engineers don't suspect. Watch through to the finale, and you'll never look at an ordinary chrome-plated faucet in your own bathroom the same way again. Chromium is a metal that simultaneously attracts with its shine and intimidates with its dangers. In pure form, it displays a cool silvery blue color, exceptional hardness, and polishes beautifully to an almost mirror-like surface. It's precisely this thin layer of metallic chromium on parts that gives us the familiar chrome look, from pickup truck bumpers to bathroom faucets. A coating just a few thousandths of an inch thick can transform ordinary steel into a brilliant, visually premium material that also resists corrosion better. But beneath this gloss hides a complex technological chain and toxic chemistry, especially during the mining and ore processing stages. The primary source of chromium is the mineral chromite. It's extracted in quarries and mines, where the rock is drilled, blasted, crushed, and sorted. Dust from the ore contains chromium compounds in various oxidation states, and some of them are toxic to the lungs and skin. So mines and processing plants require serious dust and gas cleaning systems, along with personal protective equipment. After crushing, chromite undergoes enrichment, flotation and gravity separation, to separate the valuable mineral from waste rock. Concentrate with chromium content above 45% is sent to blast furnaces or electric furnaces, where at temperatures exceeding 3,600 degrees Fahrenheit, it's reduced with carbon to produce ferrochrome, an alloy of iron and chromium. It's ferrochrome, not pure chromium, that serves as the main workhorse for metallurgy. The majority of all extracted chromium goes into producing stainless steels. If you add 10 to 26% by mass of chromium to molten carbon steel, an extremely thin but highly resistant oxide film forms on the surface. It self-heals when damaged and protects metal from rust even in humid or aggressive environments. That's how we get kitchen sinks, railings, medical instruments, and chemical reactor tanks that maintain their appearance for years. Imagine a chemical storage tank holding several thousand gallons. Adding chromium to the steel allows it to withstand contact with solutions that would have corroded ordinary structural steel long ago. Another crucial area is heat-resistant alloys. Chromium increases heat resistance and wear resistance, which is why it's incorporated into steels for turbine components, nozzles, and internal combustion engine valves operating at temperatures exceeding 1500 degrees. Combined with nickel and cobalt, these form so-called superalloys used in jet engines and power plants. Where steel must withstand both high temperatures and powerful mechanical loads, chromium is nearly indispensable. Even ball bearings in high-speed machine tools contain chromium steel, so the raceways don't break down from impact and friction. Chromite is also used without converting it to metal. It's made into refractory materials for furnace linings, where temperatures reach 3,000 degrees. A mix of chromite and magnesite aggregates withstands sudden temperature changes and contact with slag without breaking down. These linings cover the walls of cement rotary kilns, converters, and smelting units in ferrous and non-ferrous metallurgy. Chromite sands are used as molding mixtures in foundry work. They don't react with molten steel, have minimal thermal expansion, and allow casting of complex parts with high precision. One of chromium's most recognizable facets is the shine of electroplated coatings. The chromium plating process is electrolysis, where a part made of steel or another metal is immersed in a chromium salt solution and current is passed through the bath. A thin layer of metallic chromium settles on the surface, ranging from a few micro-inches in decorative coatings to several thousandths of an inch in industrial chrome plating. The thin layer provides aesthetic shine and basic corrosion protection. For example, on automotive trim, tool handles, and plumbing fixtures. Thicker layers are used to enhance wear resistance. Hydraulic cylinder surfaces, piston rods, press molds, and printing press rollers. These components work in contact with abrasive materials and fluids under high pressure, but thanks to the hard chromium layer, they maintain their dimensions and geometry much longer. However, it's precisely during the chrome plating stage and the production of chromium salts that the element's toxicity becomes most acute. Hexavalent chromium, present in certain electrolytes and reagents, is a carcinogen and can cause damage to the skin, mucous membranes, and respiratory tract. That's why modern facilities are implementing closed-loop purification systems, automated plating baths, and localized ventilation, while some industries are gradually switching to trivalent chromium or completely different types of coatings. Many countries enforce strict limits on chromium compound concentrations in workplace air and wastewater, and sludge containers are stored in specialized landfills to prevent toxic ions from leaching into groundwater. Equally fascinating is chromium's role in the colors surrounding us. This element's compounds produce vibrant greens, yellows, reds, and oranges. Chromium oxide serves as one of the most stable green pigments for ceramics, road markings, and paints that must withstand sunlight and weathering. Chromates and dichromates once provided brilliant yellow and orange pigments widely used in artist paints and printing, but due to hexavalent chromium's toxicity, their use is now strictly regulated or replaced with safer alternatives. Nevertheless, in some highly specialized materials, such as ceramic pigments for tile, chromium compounds are still used to achieve the desired shade and color stability during firing. The chemical industry relies on chromium, both as a catalyst and as an active reagent. From sodium dichromate and other salts, a wide spectrum of chromium compounds is produced, which are applied in the manufacturing of textile dyes, mordants for fixing dyes onto fibers, and agents for leather tanning. Traditional chromium tanning makes leather resistant to water, rot, and abrasion, but carries the risk of forming toxic chromium species, so modern manufacturers are transitioning to controlled processes with minimal emissions or alternative systems. Chromates were once included in anti-corrosion primers for aluminum aircraft and ship parts. They suppress the development of corrosion sites, but due to their toxicity, they too are gradually being replaced by less hazardous technologies. Interestingly, in microdoses, trivalent chromium is considered a trace element that may participate in regulating carbohydrate metabolism in the human body. But even here, the working concentration is measured in micrograms per day, and exceeding permissible levels, especially when in contact with compounds, takes on a toxicological rather than biological character. That's why chromium is one of those elements where the fine line between benefit and harm literally runs through an order of magnitude in concentration. If you look at the industrial map of the world, chromite mining centers are located in South Africa, Kazakhstan, Turkey, India, and several other countries. Ore from there travels to metallurgical plants, chemical factories, and electroplating shops, being transformed into stainless steel, heat-resistant alloys, refractories, pigments, and coatings. Products fly across the globe, from kitchens in American suburbs to oil rigs in the Gulf of Mexico, and jet airliners crossing continents at 30,000 feet. The gleam of chrome surfaces in your bathroom, or on a car hood, represents just the visible tip of the iceberg, beneath which lie mines, furnaces, electrolysis baths, and strict environmental regulations. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the fourth most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These three countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the US Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then, air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block, massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious, cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site: concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed, foundation, dam wall, turbines, and generators, comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, they use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born, not just to build, but to preserve.